My name is Nathan Hadaway, and this is my Physics 1 lab report for Lab 1, constant velocity. What is this lab, you may ask? Well, we took a cart and we momentarily pushed it along a frictionless track and tracked its movement as it moved along the frictionless track without any outside forces being applied on it, or at least with a net force of 0 applied on it. As you can see at the bottom middle of my screen, this is the video that we took. We then took this and we created a simulation for this in GlowScript. As you can see, below are a couple of the most important lines of code that I have in the GlowScript algorithm. Most of these are just defining the initial conditions, as again, there's not too much that happened in the actual lab. There was no change in forces, no change in acceleration. It was just constant velocity with position changing linearly. But I'll get more into that later. Finally, what we did is we compiled the data, seeing how the real world and simulation data compared and contrasted. Also, at the bottom, you can see is the URL for my GlowScript code if you want to look deeper into that. What is this lab trying to prove? Well, it is trying to prove that with a net force of 0, velocity should be constant. This is shown by the physics equation V final equals V initial plus F net divided by mass times delta T. Um, Again, with a net force of 0, that entire F net divided by mass times delta T is becomes 0 and is not does not relate to velocity, it doesn't change velocity. So velocity final equals velocity initial, no matter what delta t is. Again, this means that whatever initial velocity is set is the same velocity that we will see throughout the observed time where f net is equal to 0. We see this in the simulation. In the top right corner is the simulated data. We see that velocity stays a constant 0.75 meters per second. We are also proving that displacement will relate linearly will linearly increase in relation to time, or that, I guess more accurately with the equation, that distance will relate linearly in relation to time, but it could be positive or negative depending on what coordinate system is set. By the way, I set the origin to be the beginning of the track or the right-hand side of the track, and the positive x direction is facing towards the left-hand side of the track. So velocity is positive with my coordinate system, meaning that the position versus time graph will be increasing linearly over time. However, if you flipped the axis, then velocity would be negative, and the position versus time graph would have a downward slope. But we'll get more into that later. This is the actual data that was collected, the blue being the real world data that we got from the video, and the red being the simulated data that we got from GlowScript. A couple of the assumptions that I made while coding was, again, there's no friction, no air resistance, there's no net force acting on this cart. Net force is equal to 0, and that means that there's a constant velocity. This means that, as you can see in the velocity versus time graph, velocity is constant through time, which we see in the real world data as the blue line doesn't deviate too much from the red line. And in the position versus time graph, the blue line doesn't deviate too much from the red line, which is completely linear. However, if you look closely, there is a slight decrease in there's a slight negative slope generally in the velocity versus time graph for the real data. And this is because there is a very small friction force between the track and the cart, which is acting in the negative x direction or in the opposite direction as the motion, which means that velocity decreases slightly over time. We also see this in the position versus time graph, um, as there's a slight downwards bow to the blue graph in relation to the red graph, showing that there's a small acceleration in the negative direction. However, this is, again, practically negligible as the red and blue graphs are very similar to each other in both examples. Some of the frequently asked questions are, what if the axis was flipped, this being the x-axis, which I got into a little bit earlier. Basically, all it would change is it would make velocity negative and make the position versus time graph. It would still be linear, but it would have a negative slope or be facing downward. But both of them would still have the same magnitudes, which we also see as we go into the next question, which is what if you set the axis at an angle? There would be an x and y component to position and velocity. However, the magnitudes of both of these variables would still be the same, as just changing the axis doesn't change anything about what happens in the real world. or the magnitudes of what happens in the real world. How many forces were accounted for? There were two forces that I counted for: the force of gravity from the Earth affecting the cart, and the normal force that the track exerted on the cart. Both of these forces had a magnitude of mg, but they were in opposite directions, which meant that they both cancel each other out, leaving a net force of 0. Thank you for listening.